is the sixth part of Unit 5 about reaction profiles. So we have a diagram over here in which on our y-axis we have potential energy, and on our x-axis we have how the reaction is progressing, as in the reactants are converting into products. I would like to repeat that potential energy is the energy that is stored within the bonds of a molecule. And in order for the older bonds to be broken and new ones to be made, which is a detailed definition of what a successful reaction really is, one must overcome the potential energy that is stored within the bonds. When a reaction begins, the kinetic energy converts to potential energy and it successfully reaches the activation energy, or you could say that it breaks the activation energy barrier. In this graph, we have marked this area in which the bonds were successfully broken and the activation barrier was overcome. It's been called it's called the transition state. And we can clearly see that B and C, which was a single molecule, is now broken into B and C separately. And as we progress in the reaction, the products have been formed. In this graph, we can see that the potential energy of the products is lower than the potential energy of the reactants on the y-axis. It could have been higher, doesn't matter for now, but in this particular reaction, the new stored potential energy is lower than the energy that was stored before. So that means that the energy must have been released. And when energy is released, because it has to go somewhere, right? So this curve, because it's going lower than what was stored before, this means that the energy was released. And since it was released, we would say that it was an exothermic reaction. One may observe that a reaction is exothermic. It's not always observable, but sometimes it's clear. It's very evident that the temperature got hotter. If the curve was higher, let's suppose the curve was somewhere here. Let me draw this up. It was above, somewhere over here, then this would have meant that the new bonds, like the potential energy in the bonds of the product, have more energy, have more potential energy than they had before as reactants. And this would have meant that more energy has been absorbed, meaning it was an endothermic reaction. Again, one of the signs that are observable is that, your products would have a lower temperature. They would appear colder. So this is a reaction profile graph, and it's showing you the reaction pathway. And in this particular graph, you're being shown one step. There could be more steps, and we now know that in a chemical reaction, there could be more than one step. There could be 2 elementary steps, there could be 3, and it could have happened over multiple ones. What we need to know here is that every step may have its own change in heat. Change in heat, when we say that there is a change in energy, heat energy is a form of energy, and if the energy is being released, we would know that it was an exothermic reaction, and our change in heat would be negative. That means that the energy was given out, it was taken away, it was released. And released energy would be able to see it as an exothermic reaction. Could be a very exothermic reaction, could be a moderately exothermic reaction. I have just written a few of the points over here. Let's move on to the next slide. So in this graph, we have multiple steps happening. Most of the times you would be seeing this very graph, a multi-step graph on the AP test. And how do we know that? We can see that the activated complex, or we're calling it an activated complex, this entire area, and this peak is like the transition state. This is just telling you that the activation energy was reached, but in this graph you can see that it was reached twice. So it's a step two, a multi-step reaction. Elementary step one, elementary step two. The activated complex, I just told you what it is. The activation energy that took the longest time, or the highest peak, is your slowest step, as it is evidently going to take more time to reach that peak, to reach that barrier. There could or could not be a catalyst involved, and we know that not every reaction has a catalyst involved. That is not none of our concern over here. It's important to understand how the step one is different from step two. In the presence of a catalyst, this curve, not just specifically this graph, if I talk about this graph, if there was a catalyst present in the form of a graph, we would see that this particular peak that's supposed to be here just comes down to, say, here or here, whatever. It just lowers the activation energy. Okay, going back to the multi-step reaction progress. All right. Okay, so what we can see over here is that for step one, for the first elementary step, the transition state was achieved over here, meaning that the reaction happened, the older bonds were broken, and the new bonds were formed. And I can clearly see that this time, the potential energy is higher. The potential energy stored in the bonds of the products is higher than the potential energy stored in the form of the reactants. So that would mean that the energy was, I would want you to pause here and decide, basing on the previous graph, whether the delta H would be positive or would it be negative. You could think of it as what really happened to the energy. Was it added, as in absorbed, or was it deducted, subtracted, meaning it was exothermic? Okay. So you should be able to recognize which step is the slow step. We also deduce our rate law from the slow steps, if you remember from 5.3. And the step one would be an endothermic reaction. And step two, because the potential energy here is lower, it would be an exothermic reaction. We would learn more about endothermic, deciding whether a reaction is endothermic or exothermic, as in delta H plus or delta H negative. We would know about that in the next part. But it's important to know what a catalyst does to the peak of the activation energy on a graph. It obviously lowers it. Okay, so how does temperature affect the rate constant? So, when we're talking about the effect of temperature and we want to test it out, it's important that all other factors are constant, especially concentration, because that is what we have been doing in this unit. And because the concentration of the reactant, which is written in square brackets, is constant, the rate is, if you just write rate is equal to K, it would be enough. It's just simplified because your the reactant concentration is not changing. Higher temperature increases your rate constant. That just means if you look at the graph over here, as the temperature is increasing, the rate constant, the amount of product that you're yielding per second, is increasing exponentially. If you have better orientation, your rate constant would also increase. And if you can somehow lower the activation energy, remember, which is only achievable with the help of a catalyst, your rate constant also increases. At the same time, you also have to remember that temperature does not reduce activation energy like catalysts do. They only increase the kinetic energy of the particles and subsequently, potential energy, and then making it easier to achieve that same barrier. So the barrier is not budging when you're moving around the temperature, increasing the temperature. With catalysts only, it's moving. So I think that would be it. What you have to take away from here is that depending on the exothermic, on an exothermic reaction and an endothermic reaction, where would the curve be? The curve over here would be lower, going lower than the reactants, showing that the products have now less energy than before. So that means they must have released it, and releasing means exothermic. If the curve was higher, like in step 1 over here, then it would have meant that the products have more potential energy. So that means that they must have absorbed it, and that would mean that it's an endothermic reaction. For a reaction, if you can notice over here, step 1 had a higher activation energy to be achieved. Step 2 had a much lower activation energy to be achieved, and this obviously took more time. The step 1, so that should be the slow step or the rate determining step. And that's about it. Thank you very much.